Okay, here we go. Okay, so you're looking at number 1 on the blue packet. And as I often say in this class, you should not be paying attention to how to get the problem completed. That's not going to help you, because the test questions will be enough different that they will fool you if you don't understand the idea. So don't just think about us completing this assignment. The idea is to understand the concept we're trying to learn. And the concept we're focusing on today is brand new. It's this box right here. Oh, you need to correct a typo on your reference sheet. You'll have to kind of pull it back out of this sheet protector. Sorry about that. Right here on the reference sheet, I accidentally typed delta x divided by delta y. It should be delta y divided by delta x. So fix that. Well, we haven't found any other errors, but we'll correct them as we go. I've used a reference sheet similar to this in past years, but not this exact reference sheet. So that's why the typo showed up. Okay, back to number 1. So this box is a part of your reference sheet. I've added a little bit to it, but not much. The only thing I added was this little extra item here. I'll explain that in a minute. So you started learning in like 7th or 8th grade about what's known as average rate of change. And you started learning about average rate of change. So, in 7th or 8th grade, you started learning about what's known as average rate of change. That's also on your reference sheet, right there. And you learned that average rate of change means when you have a list of XY pairs, how are those XY pairs changing from one point to another? For example, if you had a list of XY pairs that looks something like this, and I'm just making this up kind of quickly here, and this pattern was consistent for all XY pairs, you would say that on average, every time the X value changes by 1, the Y value is changing by 5. That's an average rate of change. A rate of change always compares how two things are changing. So you've been studying that for quite a while, average rate of change. And it gets a little tiresome to keep saying average rate of change. So somebody came up with the idea of giving it a name, and they call it slope. But starting today, you have to change the way you talk about average rate of change. You can no longer refer to average rate of change as slope, because starting today, the word slope is going to have a different meaning. Slope starting today is going to mean instantaneous rate of change, or rate of change at a given instant, not an average over like a span. So these two boxes on your reference sheet, the two that are on the board right now, they are meant to help you understand that we are going to be constantly comparing the instantaneous rate of change of something to the average rate of change of something. Average rate of change is what you have studied in the past. We will study until about November instantaneous rate of change. Then we'll take a slight, we'll do something else for a little while, but then we'll go right back to it before we get ready for the AP test. Conrad, please.
So, average rate of change, right, is the difference between beginning and end. How can you have an instant rate of change? Like, because there can't be a rate of change at just one point.
Perfect. Two more for Conrad. What he just said is really the essence of calculus. And so I'm going to show you in a minute how Isaac Newton came up with the idea of defining the fact that, I mean, the conundrum is this. If you throw something in the air, let's get this nice, we won't throw this since it's solid glass, but if you throw this in the air, okay, as it goes upward, just say together as a class, will the object be, like the velocity of the object, as it goes upward, is it, let's talk about speed. Will the speed of the object be increasing or decreasing as the ball goes up in the air? Say it. Decreasing. Decreasing. So the speed of the object isn't constant, it's changing, and it is changing at some rate. The rate that it's changing at is the rate of gravitational acceleration. So it's changing at some rate at every single instant. Like even at a given moment, it is changing at some rate. Does that make sense? So Conrad's comment, super insightful. He's like, it seems kind of weird to say, how do you find a rate of change at a moment? Because you're like, this point right here, it's 2,10, it's not changing, but it actually is. Like if you think of it as, like if you think of x as being time, so as time goes on, this number wants to change to another xy pair. Does that kind of help? We'll keep going for a minute. Okay, so you've already studied average rate of change. We're going to start studying instantaneous rate of change. It is really important that you notice that in this box on your reference sheet, there are a few different phrases. They all mean the same thing. So those three, green, purple, and red phrases all mean the same thing. And they will test you on all three. And with a little experience, they're going to start throwing in a few other kind of ways to talk about it. Questions so far? Okay, cool. So we've got all that. Now let's talk about what it really means. So I have this Desmos graph set up to help us. So the graph you see here matches pretty well with the graph that's on the blue packet, so that's helpful. And we're going to investigate how we find the instantaneous rate of change of some xy pair. So what you see there is a point at -2, let's get some marker, we'll work on this, hold on a second. So what you see, that's the one, there we go. So right here, you see a point at -2, 1. And we're investigating how to find the rate at which that xy pair is changing at exactly that moment. Like, it helps me to kind of think of the x value as time. So just think of this, -2 seconds just means it was 2 seconds ago. -6 seconds means it was 6 seconds ago. At this moment, the value of the function is 1 right here. And that point wants to change. And the graph shows us how it changes with time. The way we're going to figure out what Conrad asked about, which is how fast is that point changing its value with time, is we draw secant lines. So this red line right here, this is what's known as a secant line. It's a line between 2 points on a curve. And the blue one is another secant line. So we draw a secant line to the right, secant line to the left. Now, calculating the slopes of those lines isn't that hard. For example, calling somebody here. From this green dot, those are big enough. Let's see if I can make them any bigger. 1 second. Oh, won't let me do it. That's okay. So from the green dot, we'll go with and for a second. From the green dot to the red dot, if we're trying to find the secant slope of that blue line, and we have to calculate how much the y value is changing from the green to the red, and how much is the y changing from the green to the red. 16, 2 for n. It's dropping 16. The y value is going down by 16. We'll go to Dylan. So Dylan, how much is the x value changing from point to point?
4.
So if we take 16 divided by 4, what do we get, Dylan? 4. But it's going down, so it's a negative 4. I have to turn this off or I can't control the board. So back here, the computer is calculating that slope for us. Like we could do it by hand, but it's a little bit easier if we just let the computer do it for us. So right here, the computer is calculating the slope of that blue line. Okay? The red one should be easy. Hands up, everyone. Who can tell me the secant slope of the red line? Hands up. What is the secant slope, or the average rate of change from this point to this point? On average, how much is the y value changing compared to how much the x value is changing? So if your hand is raised, we'll go to Susanna. What do you got?
0.
So Susanna says 0. If you knew that, give yourself 2 points as well. The computer is also calculating that right here. So the computer is calculating both secant slopes. It's finding change in y divided by change in x. Any questions about anything? Curiosity? Yeah, please.
So can you explain like what you did there to do? Sorry, in the equation.
Like here?
Yeah.
Gotcha. So what I have the computer set up to do is I have named the curve, the black, f of x.
Okay.
And I'm saying I'm going to designate a point. I call that point A. And if you look up here, got to get back to the, it won't let me draw and manipulate the board at the same time, so I have to shift back and forth. So up here, it has A. It's hard to shift back and forth there. Give me time. So here's A. A is equal to -2, just like here. So that's our point of interest. And then what the formula is doing down here is it's got this letter H. H is just another number that I can control. Right now H is set to 4. And I'm telling it, go calculate the y coordinate on f of x at A, which is -2, plus 4. So -2 plus 4, Michael, is?
Positive 2.
Perfect, right here. So it's calculating this point for me. So it's calculating the y value at that point. That's where the 1 is coming from. Getting too many markers. That's where the 1 is coming from. Over here. It is then subtracting from that 1 f of A, which is this y coordinate. So it's finding the change in y. That's what this formula is doing.
And
Comfortable?
then over h, which is the change in x.
Perfect. Over h, which is the change in x, because this x coordinate here is A. This x coordinate is A plus h. So if you take this x coordinate, subtract that x coordinate, the change in x is just the h value.
And this equation's nice because when you can just change the constant, which is h, and then you can see what happens to this.
Correct. So now I have the ability to move the points anywhere I want, and the computer will update everything automatically.
Without having like write a whole new equation.
Cool. 2 more for Michael. Anybody else? Okay. You don't need to know the details of what Michael just went through. What you do need to feel comfortable with is we are finding change in y over change in x when we calculate secant slope, just like your reference sheet shows. Questions from anyone? Oh, please.
Just something I noticed. So back kind of to the instant versus the average slope. Normally, right, it's a rise over 1, it's change of y over change of x. With an instant, won't that be dividing by 0?
Conrad, you are like You are dead on target. Dead on target. Give me just a couple more minutes. I think that will clear up a little bit. What Conrad noted was, well, let's just keep going for a minute. Okay. Other questions? Don't hesitate to ask. I might have to put you on pause, but okay. So let's keep going. So we know that the secant slope. Let's scroll this down again. Turn that off. Go back to here. Okay, so we know that the secant slope of the blue right now is 0. That's this one. And we know that the secant slope of the red right now is -4. We want to find how fast is the xy pair right here changing, this one. How fast is that changing? The way we do it is we move the secant slopes. We move those secant lines so that they become shorter and shorter, and they get closer and closer to the point of interest. The point of interest is this one here, 2, -1. Sorry, -1, 2. So it's a little hard to do it with my pen. So I'm going to come to the back of the room, use my keyboard to control the center board. So just watch up there. And what we're going to do is we're going to move the dots closer and closer to the point of interest. So this is the point of interest. We're trying to find how fast this value, -2, is changing at that exact moment. So I move this over like this. And just like Michael said, as I do that, I've set up the computer to automatically calculate the new slopes. So the computer is calculating the blue slope and the red slope as I move the dots. And this is so exciting that it's somewhat addictive. I know that sounds odd, but I promise if you were controlling, you'd have the same compulsion. You just want to keep bringing these closer and closer. You want to watch what's happening to the slopes over here. So pay attention to the blue slope versus the red slope. We'll just zoom in for me. That's not too bad. Get the x-axis to shift. Oh well. So anyway, we zoom in, and the computer is quite capable. We can get very close. Now, Conrad said something that is essential. He said, wait a minute, if you get the dots too close, the change in x will become 0. And that means change in x being 0, the average rate of change would become undefined. That is exactly correct. So what Isaac Newton figured out was, we just won't ever do that. We will make the points closer and closer, but we won't ever make the x values the same, because then we don't know what we have. And what he concluded was he defined the instantaneous rate of change as the limit of these secant slopes. And it is literally a left limit and a right limit. That's why we're showing the two from both sides. So the closer, I can't stop doing it. The closer and closer the points get, look over here at the slopes. In fact, you should see the red line and the blue line start to look like one line. They no longer look like a curve. They don't look like two different secant slopes. And look at the slopes over here. So just say it together as a class. We're finding the limit of this formula, and we're doing it, and we're finding the limit of this formula as h gets closer and closer to 0. That's what we're doing. Right here, look, h getting pretty close to 0. As I keep moving these dots, h gets closer and closer to 0. You can zoom in again. You can look at the xy pairs. Notice how close they are. This is just barely, just a little more than -2. This is just a little less than -2, exactly what we talked about in limits. But look at the slopes. The slopes are getting very, very close to what value? Say it together as a class. Say it. -2. So that's what Isaac Newton defined. That the instantaneous rate of change is nothing more than the limit of those slopes. Please.
And then would that instantaneous rate of change, that would be the same across this entire graph?
Oh,
And
awesome.
then would that change with like the amount of powers that the graph is due?
So the rate of change will be different at every single point on the graph because it's a curve. So if we zoom back out, like this, scroll forever. Yeah, we zoomed into that. So if we zoom back out and we move the point, like, think about it this way. When we zoomed in, those two secant lines became what's known as a tangent line. So as we zoom in and we bring them closer and closer together, like this, those two secant lines become what's known as a tangent line. And they show us the rate of change. Like the slope of that tangent line is the rate of change. So all I need you to say is, like when I put the cursor here, just say it as a class. Will the slope at that point, if we move the dot up there and draw a tangent line like we've just done down here, will the slope at that point be positive or negative? Say it.
Negative.
Negative. Will it be more negative or less negative than the one down here? Say it.
More negative.
More negative. So we can demonstrate that by doing the exact same thing again. You move these out, you move the point, like so. If we then make h smaller and smaller, something like this. So you can't go to 0, the slope becomes undefined. But as long as you get close, you can still calculate the slope. And it's looking like about, I'd have to zoom in. I can't tell if it's going to go right, probably doesn't go right to 10. It's probably somewhere in between because the point I picked was, if we pick A a little more carefully, we can get around, more kind of whole numbers right here. So if we pick A to be exactly 10, now it will look like the slope's going to get closer and closer to 10, negative 10. So the slope will be different at every point on the curve. Yeah. In fact, down here, I'm asking the computer to calculate the actual slope right there. So the computer's calculating the actual instantaneous rate of change, and it does turn out to be negative 10. Was that your question, Michael?
Yeah.
And you're right, if we pick a different function, different stuff's going to occur. But it won't change the idea. The idea is exactly the same no matter what function we pick. We're always just doing secant left, secant right. Other questions? Oh yeah, please, Cameron.
This is probably like unnecessarily complicated, but could the instantaneous rate of change also be considered the secant slope of 2 points infinitely close to each other?
Absolutely correct, and not unnecessarily complicated at all.
Okay.
Like I want to say it back. Okay, what he just said, 100% accurate. The instantaneous rate of change is nothing more than the slope, and you do have to count 2 secant lines. So it's the slope of 2 secant lines, secant to the right, secant to the left, that are infinitesimally close to the point of interest. That's exactly right. Good?
Yeah.
Perfect. 2 more, please, Conrad.
How do you calculate an instantaneous slope of a piecewise function, having like a point like right before a jump discontinuity?
Solid. I don't have that set up here yet to show you. I hope to get that ready in the future. I just figured this out this year. I wish I'd figured it out long ago, but learn little by little. So I can't show you, but I can give you the answer. Look up. Okay, I hope you see a little bit as to why they asked you to study limits. It's so when we get to here and we talk about finding the limit, it makes some sense to you. The reason we study continuity is that you cannot find the instantaneous rate of change at a discontinuity. Because when you try to draw the 2 secant lines, they have different slopes no matter how close you get them to the point of interest. So the derivative, which is another name for instantaneous rate of change, is not defined at a discontinuity, and that's why they had to study it. Does that make sense?
Yeah, so
Keep going, Conrad.
when we're having a question that's like find the derivative of this point, we would first analyze the continuity and then move to find the derivative.
Perfect thinking. Good news for our class, they can only make it so complicated because there's only so much time, and they never ask you to do that. They will ask questions about whether it's possible to take the derivative at a certain point, in which case you'll analyze the continuity just like we practiced in the homework. But if they usually say go find the derivative, I've never seen them ask that if it couldn't be found. It's kind of like they're just going to give it to you in a place where you can find it. At least 99% chance. That makes sense?
Yeah.
Two more, please.
Well, so I assume that like you could take like the x coordinates and then like the derivative as the y coordinate.
Oh,
and
say it
then,
again. Say it again.
Like you could make a graph, right, of the slopes of the. I mean, you could say the derivatives of a given point x as the y coordinate. So it'd be a set of coordinates that like has the derivative as the y, and then the normal x as just the normal x. Yeah, similar to like this. Would it be possible to have like a curved line in that situation? Like what would be necessary for that to occur?
Let's talk through that one. So, Michael, dead accurate as to where we want to go next. Dead accurate. Okay, here's what he just said. Look at me. You have to understand what he just said because it's exactly where we're going. This up here is the set of xy pairs that they are calling f of x. And we just showed how, at least with a computer, we'll worry about doing it manually later, how you can find the instantaneous rate of change or tangent slope or derivative of those xy pairs. You do it by finding the limit of delta y delta x, right there. That's how you find the slope at each point. Now, they came up with symbols to make it easier to talk about all this stuff. And they came up with a variety of ways to talk about it. So f of x refers to the set of xy pairs here. Look here. This is a brand new symbol. df of x over dx. You gotta see your eyes. The d does not stand for derivative. Don't ever do that. D isn't derivative. D is difference. And it's an infinitesimal difference. That's what Conrad said. He said, hey, we're just taking a secant slope, which is, find change in x, and we're making it infinitesimal, meaning not zero. Like Conrad said, that doesn't work. But if you make dx equal to, the best I can describe it is 0.000000000. Lexi's got it, 2 for Lexi. 1, okay? That's the idea of dx. dy, or df of x, because f of x represents the y values, means the infinitesimal difference in the y values. That's what this symbol means. Go find, the infinitesimal change in y, divide that by the infinitesimal change in x. And the computer does it very nicely. It's exactly what Michael pointed out. That's what this formula is doing as the x gets, the change in x gets smaller and smaller and smaller. It's just calculating the difference. Questions? Cool. Back to here. In fact, let's show something on the computer. I think it might actually help it, stick a little bit better, sink in. Let's go. Yeah, let's do this. Hold on. I have to drive from back here. So when we're finding the derivative, the instantaneous rate of change, which is right here, so we're calculating this d of f of x over dx. Look on the computer screen and watch what happens. Be prepared to answer a question here. So we're going to zoom in again. Very, very close. And we're going to get those numbers close to each other. So that means we're going to make h small. Change in x gets smaller and smaller. So making the change in x get smaller and smaller and smaller. maybe 1 might be a nice one to talk about. If I can get my hand to stop. There we go. Not too bad. Let's go a little smaller. So we can get down to 0.1. There we go. Okay, we'll try cash here. So cash, this is meant to be an easy question. How much is X changing cash from this point to this point?
0.1.
0.1. We set that up over here. So we're good there. That's how much the X is changing, 2 for cash. Let's go to Kayla. Kayla, I don't expect you to do the math perfectly, but can you tell how much, like the Y value is? It's kind of hard, I guess. What I was thinking? Like the X value is changing by 0.1. The Y value is going from 49 to roughly 50. So how much is the Y value changing, Kayla?
1.3.
Yeah.
1.003.
There we go. It's hard to see because the computer doesn't blow it up big enough. It's actually 1.005. So we'll just say close to 1, right? So look, hey, 2 for Kayla. If the Y value is changing by 1, and the X value is changing by 0.1, just say it as a class. What's 1 divided by 0.1? Say it. That was a little weak. What's 1 divided by 0.1? 10. Yeah, the slope is 10. It's more precise than that, but that's the idea. As you get these closer, it gets even closer and closer to 10. So back to here. So that's all we're doing. That's all this symbol means. 1 second, Conrad. Change in Y divided by change in X on an infinitesimal level. This symbol means the exact same thing. Right there. Go ahead, Conrad, please.
Is there any causation whatsoever in the fact that the point at -2 had a slope of -2 and the point at -10 had a slope of -10?
Let me come back over here. Oh, no, that was just
Pure luck.
coincidence for this particular curve. Good comment. This curve has a lot of symmetry in it, so things like that are likely to happen, but no discernible pattern for, in general. Please.
This is maybe not super important, but why is it the secant? Why do we call it secant? Like,
Oh.
what connection does that have?
Good comment. No. 2 for Mary. So I believe there is a connection. So I have to confess my ignorance. I believe there is a connection between the fact that we call this the secant slope and the trigonometric function known as the secant. But I don't remember the connection because when someone explained it to me, I'm like, wow, that's a long stretch. Like it didn't feel like, oh, that's intuitive. I can remember that. So I just purposely chose not to remember it.
Okay.
Is that okay?
That's good then. That's great.
The same thing with tangent. The same thing with tangent. Someone explained to me why this is called tangent slope and how that connects to the trigonometric function known as the tangent. And I'm like, that is not an obvious connection. So I'm just going to not worry about it. So sorry about that. But
No, that's great.
anybody else? Gavin's having a rough time back there. There we go. Kind of awake. Anybody else? Tom, please.
So we found the instant rate of change using the Desmos and the computer. So are we going to find out how to find the instant rate of change just like not using a computer now?
Awesome. 2 more for Tom. What we'll do in Unit 1 is we will not, everybody looking at me? We're not going to worry about calculating the instantaneous rate of change to any sort of precision. All you have to be able to do in Unit 1 is the following. You have to be able to look at a curve and answer this. Just say it together as a class. Right here, if I drew a tangent line. So I used the computer to hopefully, make sense of what we're doing, but we don't have to get that precise yet. So if I draw a tangent line right there, that blue one, just say it as a class, is the slope of that tangent line positive or negative? Say it. Negative. Perfect. If I draw another tangent line here, is the slope of that tangent line positive or negative? Say it. Negative. Is the green more or less negative than the blue? Say it.
Less.
Perfect. Less negative. If I draw this tangent line, that's a tangent line of 0 because the slope is horizontal. And then this tangent line would have a positive slope, do a different color, blue, I got blue or purple. So there's a positive slope, and then here's a black one, more positive. That's all we have to do for Unit 1. The actual calculation of the slopes comes in Unit 2, but we will get there and be able to do it without the computer. Does that answer your question, Tom?
Yeah.
Good question. Anybody else? Solid. Oh yeah, please, Ann. Not Ann. Okay, we gotta start a new tradition. I've done this for years as well. I should know your names by now. I should not be messing up. So Nixon gets a extra ticket for misnaming. Sorry, go ahead, Nixon.
I had an important question and I sort of remember it. Can we go back to the graph on Daniels? I think I remember what I was trying to say. Oh, yeah. So the instant rate of change is 10, negative 10. Is
So let me say it back to you. So I've got a word on the board up here. The video can't see what I'm pointing at, but the word is of. And Sadie Edwards made that for me. She promised she'd make me a nice sign, but she didn't quite get time. So anyway, we have the paper one still. I'm a shameless beggar for signs because I literally like remembering you. And so if anybody wants to find the time to make a nice framed sign with the word of, definitely will go on the wall with your name, and you'll be pointed out forevermore for years to come. Anyway, it says of. The key thing Nixon's got to do is this. From this day forward, it is so essential that you use the word of frequently, because otherwise our conversation gets very confusing. So the way I say it back to you, Nixon, is this. The tangent slope of this point right here is going to be negative 10. Now, I kind of interrupted your question again, but I don't know if that was your question.
Well, the tangent slope is the instant rate of change, right? So it's negative 10. Okay.
Let me say it back to the class because you're right on target. If I say the tangent slope of f at x equal, whatever that was, at x equal negative 10 is 10. Sorry, it is also negative. That's weird. That was just coincidence, by the way. The slope here at negative 10 is also negative 10. That means the same thing as saying the instantaneous rate of change of f at x equal negative 10 is also negative 10. They mean the same thing. That's why I put them in the box together. Is that your question? Two more for Nixon. Anybody else? Awesome. Okay. We were talking about Michael's question. We got a little bit off. We got to get back to his question. Here's another symbol. Look. This one I don't like as well because it doesn't show any meaning. This shows meaning. It shows I'm taking a rise over run. I'm finding the change in y divided by the change in x. I'm just finding a slope. The slope meaning is hidden here, so don't like that symbol as much, but we are forced to use it because the world uses it. And it means the same thing as these symbols. That's why there's equal everywhere. Questions? And complimenting Cameron one more time, this is what Cameron said. When you find the instantaneous rate of change, you're finding nothing more than the limit of a secant slope. Like when the secant slope gets infinitesimally short. Okay, so back to Michael's question. So here's what we know. Let's clear this off and start a little fresh. We know if we look at this graph up here called f, we could go to, let's go to the easiest point. We're going to go right here, and we'll get Lupita to help us. All I need you to tell me, Lupita, is what is the xy pair of that point on f? Perfect, other than just the other way around. 0, -1. No worries. Two more for Lupita. Anybody else? Awesome. Okay, that's the point on f. Well, as of today, you have a new thing you can add to the graph at that moment. You can say, oh yeah, I also learned today that the tangent slope right there, so the tangent slope right there, this is not allowed on the AP test, by the way, that's just my way to abbreviate. The tangent slope right there is also 0. So this 0 has a different meaning than this 0. This is the x value of the xy pair. This is the tangent slope or instantaneous rate of change at that moment. Conrad, please.
I just had a question. So for limits, right, we've worked on limits before. There's the left-hand limit and the right-hand limit. And if they're the same, then you get just the overall limit of that point. With this, we're finding the derivative or the other newer thing that we're doing. Both of the examples so far, they're not quite the same.
Oh, it's exactly what we actually studied in the buff, pink, and yellow packets. In all those packets, the left and right limits were actually never the same. Well, back up. The actual values were never the same, but in the limiting sense, the limits were equal. And that's what's happening here, is the idea is that, yes, when h is 0.0092, this slope is not identical to that slope. But as h gets closer and closer to 0, these two slopes get closer and closer to being exactly the same. They are actually never the same, except in the infinite sense. So if you go all the way, so you can't go to infinity. I don't know how you explain that. But that's what Newton defined, was if we really kept going forever, they would be the same. And that's how we resolved that conundrum kind of the, Isaac Newton's famous for the apple thing, right? Whether that's true or not, I do not know. But a falling object, like an apple or a glass ball, don't drop it, it's heavy. As it falls, it's going faster and faster. So its velocity is changing at every single moment. And what he reasoned was he could never calculate the velocity at a given moment. All he could do is calculate the velocity for the moment before and the moment after, and get them shorter and shorter and shorter. And he decided that's what we will call the instantaneous velocity. Have I answered your question, kind of?
Yeah.
It's very heavy. Okay, I should probably take it away. It'll be very distracting. Okay. Another gift from some students, very kind. Okay. So back to here. All right, so we know the tangent slope right there, the instantaneous rate of change is 0. We now have a new way to write it. So let's show that. Move this out of the way a little bit. So we can write this. We can say, yeah, that's good. And you have to know this notation. We can say the instantaneous rate of change, that's what this is, of f with respect to x at an x coordinate of 0, like that, is going to be, in this instance, 0. Yeah, please.
So the line is saying at whatever the thing is?
Correct, because the instantaneous rate of change of f will be different at every x coordinate, theoretically. We must specify what x coordinate we are speaking of. Back to this word of, how important it is. So that's the purpose of the bar. Two more from Michael. Conrad.
Just a question. So you're talking about the notation for this, and I think you mentioned this, but I'm not certain.
You're good. Keep going.
For multiple choice questions, do we need to show notation?
No. So for multiple choice, you simply have to read what they wrote and understand what they're saying.
Yeah.
So they could end up using that notation. Two more for Conrad. They could end up using this notation here. These are all just what I showed you in the box. Oops. Yeah, that's right. So they could use this one, or they could use this one. And on a written test, you will be expected to use one of them as well. There's not typically a requirement for which one you have to use, but you have to be familiar with them. So, yeah, please, Mary.
Sorry, so the second equal sign is saying that's, so the first one, what's the like, I guess.
I think I know your
word
question.
meaning of.
I think I know. I'm going to try. If I'm wrong, you speak up again.
Okay.
So what this is saying is the instantaneous rate of change of f, which means how fast the y values change compared to the x values, at specifically an x coordinate of 0, that instantaneous rate of change at that specific point has a value of 0. So it's like this, Mary. The little equal here is just referring to what x coordinate we're speaking of. The equal sign here is talking about the rate of change. So the rate of change, I should have chosen different spots. We have so many zeros. Does that answer your question?
Yeah, so would you usually write the x like smaller and lower down, and then the bigger 0 up, or is that just how you
Yeah, when I
do it?
typed it, it gets kind of spread out.
Okay.
If I write it by hand, I would do it like this. I would be able to make it a little bit smaller, but still kind of bulky. That's why somebody invented the other notation.
Okay, thank you.
Does that help?
Yes.
2 more, please, London.
I was just wondering if the difference in fx over the difference in x, that's like around your x equals 0? Is that like the left and the right of that?
No, it's perfect, London. Like, that's why we did the Desmos thing. So you could kind of imagine that we're doing this. We're going on this graph. And I gotta do it now because I got all excited. We're going on this graph. We're gonna go to x equals 0. So we'll zoom way out. Move the dot down to x equals 0. Come on, computer. Steady hands. There we go. When we do that and then we change h and make it smaller and smaller, the secant lines get closer and closer to a single line. They look more and more like the tangent line. And then we are calculating the slope at of that tangent line. And that's why that slope right there is getting closer and closer to 0. Is that your question, London?
Yes, thank you.
Eliza, please.
This is probably a stupid question.
It is not.
All the examples you just showed us so far, the tangent slope is equal to the x.
Total coincidence.
Total points.
Total coincidence.
Just double checking.
I need to fix that. That really isn't supposed to, well, it just kind of happened. I didn't even notice, so. Is that okay? Does that answer your question?
Yeah. Thank
2
you so
more.
much.
You're welcome. Anybody else? Yeah, please.
Is there any way you could show us do you have an example of where the tangent slope is not equal?
To the point. I don't know. Let's find out. Hold on. Unfortunately, not in this graph. So they gave us a graph on this blue graph has that characteristic, where everywhere I pick an x, the slope's going to match. But lots of other graphs won't. So that was just, I tried to match the blue one to just kind of make it easier for you to think about it. I didn't notice that they had done that on the blue. So, anybody else? If you change the formula for the curve, the slope, that will stop happening. So, please.
So like on paper here it says like finding the slope at every point, not just one point. So how would we find the slope at every point?
Perfect.
Every point is changing.
2 more for Kayla. So, and really, because it's just a matching exercise, Kayla, we don't technically have to find the slope at every point. Just enough of them to see where the match occurs. Does that make sense? They won't ever ask you to find, well, in Unit 2 we'll learn how to find the slope at every point in a very efficient way. The way we're doing it right now is not efficient. But it's just a place to start. So, good for now. 2 more for Kayla. Okay. Oh, and one thing to put your mind at ease. No one is supposed to go home and try to do this pocket yet. Okay? Like today is, let's start talking about it. let's start talking about this idea of instantaneous rate of change. Let's learn what it means. That's today. And then you'll come back on Tuesday after the Labor Day holiday, and we'll talk more. That's good news for Kayla. Then we'll talk more, and then we'll get going on work on the packet. Okay? So don't stress yet about the packet. If I put a due date on this, it's going to be a bit out. So, okay. But back to the question. Okay, pull this out of the way. Pull this out of the way. We know that. You know what's going on there. We're just going to use this one for a second, like that. Okay, so we know that. Another way to look at it is like this. I think this is what Michael even said earlier as well. Pull those out of the way. Think of it as a table. So we're going to get, see what I'm not called, I'll get Lexi to help me real quick. Lexi, this is meant to be easy. If we're looking at this dot right here, what do I put here and here, Lexi?
Zero, -1.
Yeah, everybody does it backwards. 2 for Lexi. Everybody okay? Cool. So let's go to Keely. What do I put here, Keely? 0. Because we figured out that this means 2 for Keely. This means the slope of this point on F. And that slope is also 0. That's what we figured out. Please, Conrad.
So, looking at the question, right? The graphs that are the answer, is the correct answer supposed to be a graph of x and then f prime x?
Perfect. I'll say it back to the room. 2 more for Conrad. These 2 columns here, these are the xy pairs you see in this picture for F. But then these 2 columns over here, this one and this one, those are the xy pairs, and I think Michael said this earlier, of the graphs below, the F prime graph. F prime graphs, okay? So, everybody in the room is going to answer this. According to our analysis, we should find an F prime graph who has an xy pair of 0, 0. That tells me right away one of those 4 is wrong. Raise your hand if you can tell me which one must be wrong. It doesn't match. It cannot be the F prime graph of that F function. Which one is wrong? Most of you. Let's go, Dylan Bashane, please.
The one that has a straight, the linear one.
Over here.
Yeah.
2 points for Dylan. You're making a mistake, but tell me how what you're thinking is so I can help you see your error.
Prime, I'm like half asleep, so I'm sorry.
Oh, no worries. Do your best.
Because it's prime, it would just be inverted.
Oh, no. 2 more, though. So hands up again. Who knows? Okay, this chart tells me that on the F graph, I should find an xy pair at 0, -1, and I do. But this chart also tells me that on the F graph, I should be finding an xy pair of 0, 0. Sorry, on the F prime graph. So that tells me one of those 4 is wrong. Who knows which one is wrong? Hands. There we go. Trevor, which one?
The first one.
So A is incorrect. How many knew? 2 more. Because this dot is 0, 1. And the F prime we need must be 0, 0. Oh, please.
How did you know that f prime of x is 0?
Awesome. So here's F. 2 for Ella. I went to this point on F, which is right here. And I imagined that I was using the Desmos program. And I was finding the tangent slope at that point, where I would do like a secant to the right and a secant to the left. But then I move the points closer and closer. As I do that, the secants do this. And eventually they are flat, and a horizontal line has a slope of 0. Can't tell if that helped, though.
Like makes sense, but I still don't.
We'll leave it alone for a minute, and we'll maybe talk again later. But don't stop asking if it still feels fuzzy. This really is fundamental for the next several weeks. But if it feels fuzzy, hold for a minute. Tom, please.
So would
Two more for Ella.
graph that could represent the slope at every point BT?
So, here's what Tom did. Two more for Tom. He said, look right here. Tom, what's this XY pair?
0, 0.
So far, so good. We're supposed to have at x equals 0 on the f prime graph, a value of 0, and we do. At x equals 0, the f prime graph is 0. That's a dead match for those 2 points. As Kayla said, ideally we're supposed to find a match for every point. But because it's matching, we can just do a few and be good enough. So let's try another one. Tom's right, that is the correct answer. Let's go over here. Let's go Eliza Lynch. Eliza, just do your best. What XY pair does that kind of look like?
-2, 1.
Perfect. -2, 1. So we're going to erase and start over here. So we have a point, 2 for Eliza, at -2, 1. Come on. -2, 1. And at that point, if we did the same thing we did with Desmos, this is back to Ella's question, we would eventually find that the slope of the tangent line would look something like that. When you make the 2 secants get shorter and shorter. So we'd be wanting to find that slope. Say it as a class. Get ready. Is that slope positive, negative, or 0? Say it.
Negative.
Negative. That's all we really need so far. Like Tom asked earlier, we don't have to go further than that. Just it's negative. So there's a negative slope. Well, that means the y value on f prime when x is equal to 2 is supposed to be a negative number. And it is. That works. This, in fact, right here, Emily Harmson, roughly tell me the XY pair right there. Perfect. That means that up here, this needed to be a -2. The slope, it's telling us if this is the correct match, then the slope up here at x equal -2 has to be this value right there. That's the connection you have to keep making. The y values on this graph are telling you the slopes on this graph. That's the connection. Super fundamental. You will never stop using that all year. Okay? Questions? I feel like some people asked questions I may not have answered them. Is there any question that got left hanging? I don't want to leave you hanging. No, okay, I guess we're good. So far that works. That means this one would not work. Because right here, Eliza Bills, what's that XY pair, Eliza?
That's going to be -2, 2.
So that's -2, +2. Seeing a lot of 2s later. 2 more for Eliza. That's completely wrong. This -2 is the same meaning as this -2 right here. And at this spot, this slope is certainly not positive. So that one is wrong for sure. Please.
If you were to like flip that graph upside down, then it would be the opposite, right? So that would be correct, yeah.
Yeah, Michael's correct. If this right here is f, this is f prime. Yep. Questions? Your questioning is really good. I gotta do all I can to keep encouraging the questions. Makes a huge difference. Because I can explain this 12 different ways. I'm trying to find the way that makes sense to you. And the only way I can do that is if you keep asking. Cameron?
I have like less of a question, but like kind of like a practical explanation in my brain that I use for like with Elle's question about like why that one point had a slope of 0 is like if you put like a rubber ducky in like a thing of water and you like push it down a certain depth or whatever, it'll shoot back up because it's buoyant. So on this graph, I like to think of like if I somehow shot the rubber ducky down, it would have a speed that increases until it's the water and then slows and slows until it eventually stops moving, which is at its bottom. And then its buoyancy force will carry it back up and then it speeds back up. So at some point, as it reaches its farthest depth, it is no longer moving, which would be that 0 point, but then it speeds back up as it goes back to the surface.
If it helps, go for it. Cool. No, really.
You would love physics.
More for
I don't know if
cameras.
that helped
That works for
anybody,
you.
but
It helps you a ton.
probably.
He really just sounds like
To be fair, I would have to sit with you a little longer to go, because I'm not the fastest thinker in the world in skate. I got to follow this analogy because I'm not quite following it. But no, don't stop thinking that way. Like, it really does help. Kayla, please.
So, I was just kind of glancing at the next problem. It's the same, like positive, negative. It's just a bit sharper. So should our answer still be the same? Because it doesn't. We're not looking at that right now. We're just looking at where it's positive and where it's negative and where the x prime is.
Oh, awesome comment, Kayla. Let me say it back to you. You are correct. You're not typically, I have to say typically, there's always that 1% chance we've got to get a little deeper. And next time I will show you one where we've got to go a little bit deeper, but not a lot deeper. We're just looking for general trends. So where I like to start is, this is F. This is supposed to be easy. Raise your hand and tell me, at what x coordinate is the slope of F0? Hands up. At what x coordinate? Just raise your hand. At what x coordinate? If Cameron's analogy helps, use that. If not, I just use tangent. Apparently it doesn't help Ann. No worries. Don't stop sharing, please don't. It really is important that we just keep talking about it. It's super important. Hands up. Where is the tangent slope going to be 0, Ella?
Isn't it like negative 0.5 and 0.5?
Negative what?
0.5 and 0.5.
So if I go over to negative 0.5, that'd be about here, and it'd be about here. That slope will actually be something negative.
I was thinking of the x points, but not okay. Now I see what you're talking about.
So no more 2 for Ella. Hands up. We gotta hurry a little bit. Look, where is the slope going to be 0? 0. So it's right here. So the first thing I do is look for a point. We're gonna have to quit. But you're on the right path, Kayla. That you're not looking for super details, just generalities that will give you a match. If we need more, we'll worry about it later. But okay, so no homework really. If you want to try some of these, you can, but we haven't gotten very far at all. Like we talked about those, and there's several more concepts we still need to cover, like the reference sheet. We talked about 2 boxes on the reference sheet. We have not talked about any of the ones above that. Those are all needed to do the rest of the blue packet. So we'll work on it on Thursday. Have a good break. See you.